And
good evening, everybody. This is the public event that's attached to the Forming and Exploring Habitable Worlds meeting here in Edinburgh. I'd like to say a big thank you to the sponsors of our overall meeting, which includes the UKRI's Science and Technologies Facility Council, which is a funding agency, the Royal Astronomical Society, the European Association of Geochemistry, the Scottish Alliance for Geoscience, Environment and Society, the Meteoritical Society, the Geochemistry Group of the UK, ZEISS and its microscopy section, New Amatec, and of course also Frontiers in Geochemistry. And of course, I'd like to acknowledge the team behind this meeting. There are many people involved in organising and delivering the overall conference and also, of course, the public event. In particular, we're kicking off this evening with our Let's Explore Planets event, which is aimed at younger audiences. We have two presenters here, Professor Nicolle Zellner, who's visiting from Albion College in the USA. Nicolle is the recipient of the 2021 Carl Sagan Medal of the American Astronomical Society, which marks her extensive contributions to outreach. We also have Associate Professor Elizabeth Tasker, who's visiting from the Japan Aerospace Exploration Agency, otherwise known as JAXA. Elizabeth was an earlier winner of the Daily Telegraph Young Science Writers Award, so we're hoping that there are young, interested writers out there. She recently authored her first popular book, The Planet Factory, and now I'll pass over to Elizabeth to kick off the evening. Thank you. Stop sharing. So, have I stopped sharing? Yeah.
Thank you very much. So today, I would like to get control of my slides. So today, what I'd like to talk about is some worlds that we've discovered that might be incredibly alien. And I'd also like to talk about what should have been, but was not, the first detection of a planet outside our solar system. So I'm going to start with what I hope is a set of planets we're all familiar with. This, of course, is our solar system. So around our own sun are four small rocky worlds: Mercury, Venus, Earth, and Mars. And then a bit further out are four very large gaseous planets: Jupiter, Saturn, Uranus, and Neptune. And just so we're all on the same page, you are currently on Earth. Now, until almost the early 1990s, these were the only planets that we knew of. However, we never thought they would be the only planets out there. So, beyond our solar system, there are what we call extrasolar planets, where extra here means outside, and solar means the sun. So an extrasolar planet is a planet that is not orbiting our own sun, our own star. Now, before the discovery of the first exoplanets in the 1990s, there was another possible discovery. So the year is 1988, and a star called Gamma Zephyr is showing a strange wobbling motion. It seems to be making a tiny orbit, wobbling backwards and forwards. And it was suspected that this strange wobble might be due to an unseen gravitational force. You know, something small, too small to see, but that had enough mass to pull on the star. And as it orbited the star in response swayed back and forth very slightly. So, could this be an exoplanet? Could this be the first planet we've ever discovered around another star? Well, people were skeptical. One of the problems was that Gamma Zephyr was not alone in the sky. Gamma Zephyr had a sibling. This is a binary star companion. Now, binary stars are when you have two stars that orbit one another in the sky. And this was a bit suspicious because very notably, our sun, the only star at the time we knew had planets orbiting it, doesn't have a binary companion. So is it even possible for a star that's in a binary with this stellar sibling to have planets? People weren't sure. The second problem was that Gamma Zephyr was thought to be a giant star. Now, a giant star is what happens as a star nears the end of its life and it becomes very big. And as it becomes big, well, it becomes a bit grumpy. And as it becomes grumpy, the outer layers of its atmosphere start to pulsate. You know what a pulsation really looks like? It might look like you're swaying backwards and forwards as if there's a planet orbiting around you. So was this really due to an unseen gravitational body, or was it just that this older star was feeling a bit bad-tempered? So on the whole, people went, oh, no. And they published a paper saying, sure, there is a wobble around this star, but it's not likely to be a planet. And when they published that, they missed discovering the first exoplanet, because it turned out this wobble was absolutely due to an exoplanet. But that exoplanet was not confirmed until 2003. So it should have been the first exoplanet, but it wasn't. And I suspect everyone is very annoyed by that. So what went wrong? I mean, this would have been the biggest discovery, like the first planet outside our solar system. Does it get more exciting? It doesn't, people. It does not get more exciting. So why were people so conservative and worried that they would be wrong? Well, to understand exactly why they were so worried, we need to look at how planets form. Now, young stars are surrounded by disks of dust and gas, and this is a real image of what those disks look like, taken by the ALMA telescope. And in these disks of dust and gas are tiny, tiny grains of dust that start to stick to make something bigger. So if we take a more cartoon version, here's our young star, and it's surrounded by this disk. And in this disk are tiny little grains of dust. And these are going to collide, and they're going to get bigger and bigger and bigger. And eventually you get something that starts to look like a planet. Now, that seems quite straightforward. However, let's take another look at the system. We're now going to look top down. Here's our star in the center. Here's our gas disk. And those little gray dots are our rocks that are going to hit each other and get larger and larger to become a planet. And now we're going to throw another star into the system. This is the star sibling. What happens now? Well, these little rocks, primarily, most importantly, they feel their star's gravity, so they're pulled towards the center. And that means they make nice circular orbits as it happens, just like the moon around the Earth or the Earth around the sun. But now you've got a second star in the system, and that's also got some gravity, and it's going to pull on this system. So there you are, trying to walk around in a nice little circle. But you've got someone really annoying, your sibling, your brother or your sister is standing there holding on to you. So you're trying to move around in a circle, but you can't quite do it because you're being dragged on by your brother or sister. And that causes this disk to bulge out towards this second star and create a drag force. And this drag force slows down the gas because your younger sibling is just tugging on you all the time. So you start going slower. And as you go slower, actually what happens is the disk shrinks. So that gives you less space and less time to form planets. And it gets worse. Not only is that disk being pulled on, but as you try to form a planet with these rocks sticking together, the rocks get pulled on at the same time. Now, at this stage, we call these rocks planetesimals because they're not quite planets, but they're bigger than rocks, so planetesimals. And these are also being pulled by the second star. And that means rather than making nice, tidy circular orbits, they end up on wild, reckless elliptical orbits. And that turns out to be really bad for planet formation. So if you imagine you're in a bumper car and you're going along and someone's coming along beside you at roughly the same speed, if you hit them really very gently because you're both moving at the same speed. And that's great for sticking. Two things come together, same speed, very gentle, great. You stick and you build a larger object. Fabulous for planet building. Now, if you're on an elliptical orbit, well, your speed could be anything. So you end up with these much harder collisions that slam into each other. And rather than sticking and building up a nice planet, you rebound. So it's really hard to build up a large planet if you have these very hard collisions at different speeds, and that's a major problem. So that's why people thought having a stellar sibling was generally not a good idea if you wanted to form a planet. And actually, they were right about that. So the Kepler Space Telescope, which is one of the greatest planet finders of all time, looked at stellar siblings in the sky and said, do you have planets? Have you managed to do it despite having a star sibling? And the answer was, well, it's not great for your health to have a sibling, which, let's face it, we all knew. Siblings are very annoying, but it comes down to distance. If the two stars are far enough apart, by which I mean more than 1,500 times the distance of the Earth and the Sun, then actually it's not a problem. Your brother or sister is far enough away, they're not going to disturb you, and you can both form planets and live happily ever after. However, if you're closer, it gets a bit messy, but that does not mean it's impossible. It's just more difficult. So, to recap, if you're hundreds to thousands times the distance between the Earth and the Sun, generally speaking, you can both have your nice gas disks around you, form some planets, and be very happy. If you move these stars closer, so now they're about 10 times the distance between the Earth and the Sun, that's still in our solar system. So we're talking distances to maybe Uranus. If you're that sort of distance apart, well, one of you gets planets and the other one doesn't. So the favourite sibling gets to build planets, but its other sibling, much more difficult. Now, if you get closer still, so now you're actually only roughly the distance between the Earth and the Sun. So imagine replacing the Earth with another star. What happens then? There isn't enough space for a disk to form around either star, but it can actually form around both stars together. So now if you're a planet, you actually orbit two stars, not just one. And this might remind you of a very, very familiar system, I hope. It is actually the setup of Star Wars' Tatooine. And I hope that people in the audience still remember Star Wars, otherwise I will feel very old. But in Star Wars, the lead character, Luke Skywalker, is born on or lives on Tatooine as he's growing up. And you see these two stars in the sky. And this is the system for this planet. It's a planet that orbits both the stars at the same time. Now you might say, okay, fine, but let's face it, Star Wars is fiction. Could you actually have a planet that orbits two stars and could be habitable? Now, unsurprisingly, that is a complicated question. And I know Nicole's coming up next to talk about habitability in a bit more detail. But I'm going to consider it very simply. I'm simply going to ask, how much sunlight would that planet receive? Now, if we consider it purely based on sunlight, we can define something called the habitable zone. And this is the amount of sunlight the Earth needs to keep liquid water on its surface. So if the Earth orbits anywhere inside the habitable zone, we can keep our oceans and seas. And so I'm just going to wave my hand and say, therefore, we're habitable, because we know water is important for life. So with this very simple approximation, what happens when you've got two stars in the sky? You're now going to get starlight from both these stars. What happens to your habitable zone? Well, if you just have one star, the habitable zone is top down, it looks circular, it's actually spherical. So you have a nice round area around the star where you receive just about the right amount of starlight for water. Now, if you have two stars, but they're roughly the same mass, that habitable zone squishes and it looks more elliptical because now you're receiving twice the amount of sunlight from two slightly different positions. If you have two stars, but they're not the same mass, so one is very bright, but one is dim, you can end up with an almost circular system, but with kind of a bulge off to one side, which represents the added light coming from that star. Now, you might look at this and think, well, sure, it's a bit more complicated, but I could draw a nice orbit that sits in that habitable zone and, you know, it's got a good amount of sunlight. I think I'd be okay there. I could, you know, live quite comfortably. And you might be right, but you also might be forgetting something important. And that is, those stars are not stationary. So those stars are going to orbit one another as you orbit both of them. And that means the habitable zone, it changes shape while you're orbiting. So you might start off in the habitable zone, but do you stay there? So for example, here's a planet that sits on the edge of the habitable zone. And if you watch it, it's okay for some of its orbit, but then it drifts outside for part of its orbit. So during some of the year, your planet's habitable, and during other parts of the year, suddenly it becomes inhabitable. So could life even survive that? Could that system even exist? Well, the system can exist. So in 2011, a planet called Kepler-16b was discovered. Now, this is not a habitable planet because it's not rocky. It's actually roughly the size of Saturn, so roughly 100 times the mass of the Earth. But it does have two stars. So it has a bright star and a dimmer star. So its habitable zone looks a bit like this. Now, if we switch to this diagram, this is an actual simulation. So the green zone is your habitable zone. The two black circles represent the motion of the stars. And if you can just about see at the edge of the green zone, there is an orbit of a planet. And so what happens is during this orbit, the planet slides in and out of the habitable zone. And if you consider the temperature change, it might be roughly a change of 15 degrees continuously as that year goes on, just based on the amount of starlight it receives. Now, you might still think that doesn't sound so bad. I mean, difference between summer and winter, that's more than 15 degrees. But this isn't a local change. This is a global change in temperature. And to realize exactly what that might mean, there was a little ice age back in the 1600s, and the Thames in London froze. Now, I've certainly never seen the Thames froze even come close. The global temperature change during that little ice age was just 1 to 2 degrees. So can you imagine how much the planet would change if the temperature changed by 15 degrees several times? I mean, 4 to 5 times during the year. That would be some crazy weather. So could life survive? Well, we don't know, but it's not impossible. Maybe life would hibernate during the inhospitable spells. And therefore, if you were on Tatooine and this was the situation, then, you know, the force would awaken in about 6 months when the planet becomes habitable again. And then during the rest of the time, it would have to sleep. So what else can a binary sibling do? Well, here's another example. This is the 55 Cancri system. And it's exciting because it was the first discovery of a 5-planet system. And it does have a binary star, but it's a small one. And actually, it's over 1,000 times the Earth-Sun distance. So it's not really causing any problems. The planets are formed quite comfortably. We're all pretty cozy. But it is having an effect. So what this star does is actually, it turns the system on its head. And it's slowly rotating the entire planetary system upside down. Now, gravity-wise, that doesn't affect you. You stay stuck to your planet. But if you were to look at the night sky and you had constellations like this, over time, you would see them slowly turn upside down because your whole system is rotating. Now, it takes a long time. I think we're talking 33 million years or something. Yes, it's not fast. But if you were to live that sort of length of time, you would eventually see the stars turn over. Now, this system, it surprises, doesn't end. A particularly surprising planet in the system is the innermost one, the one I've coloured in pink here, 55 Cancri E. And this was a strange planet because both its radius and mass were measured, and it was discovered it was too dense to be a gas giant. But it seemed too light to be an Earth-like world. So what's it made of? If it's not rocky and it's not gaseous, it's not like the Earth and it's not like Neptune, what is it? Well, there were some exciting ideas. What is a substance that's heavier than gas, but lighter than rock? Well, liquid. So could it be a water world? Could there just be huge quantities of water on this world that gives us this intermediate density? Well, there's a problem with that. And that is the orbit of this planet. So the time it takes for 1 year to lap the star once is 18 hours rather than our 365 days. And the average temperature of this planet, because it's so close to its star, is around 2000 Celsius. So we wouldn't really expect water in those conditions, would we? Because we know it becomes steam at around 100 Celsius on Earth. However, this planet has a much higher mass than Earth. And what that means is, in addition to the high temperatures, you get a very high pressure pushing on that water. And that allows a very, very strange form of water to fall. So rather than liquid and rather than steam, you can get a form called supercritical water. And it's not really a liquid and it's not really a gas. So if you are able to survive on this planet, which you're not, to be clear, I do not recommend going there. But if you could survive, you might find yourself in this supercritical fog where you can't quite tell whether you're in the sea or if you're in the air. It's a sort of in-between strange form of water. So that's one option. Option two is the planet is made of something slightly different compared to the Earth. So if we consider the Earth, left here, our core is made of iron and nickel, and the rest of the planet is more or less magnesium, iron, silicates, rock. So maybe we could just change these elements slightly and make it a bit lighter. So could we do that? Well, there were clues that we might be able to. Initially, when 55 Cancri, the star, was observed, it was found to contain a lot of carbon. Now, our sun also contains carbon, but this star was thought to be particularly carbon rich, and that would be passed on to the planets, who would also form with a lot of carbon. Now, if you form with a lot of carbon, you do get slightly different minerals and rocks. So in particular, you could get a surface that was made of the kind of graphite, like what you have in pencils. And inside, you get silicate carbide and carbon, which doesn't sound very exciting, except that as the pressure increases, this is crushed into diamonds. So you could have a diamond world with a diamond interior and a sort of pencily graphite exterior. And if there was any liquid at all on such a planet, it would be tar. Pretty unpleasant, but kind of cool at the same time. However, later observations suggested this star wasn't so carbon rich, which means this scenario maybe isn't so likely. But another weird thing was observed. Now, before, we'd seen planets detected because the star was wobbling, because the gravitational pull of the planet was causing it to swing to and fro. There is another way of detecting a planet, and we call this the transit technique. And what happens here is the planet passes in front of the star's surface, and as it does, it obscures a tiny amount of light. And if you can detect that drop in light, you can detect the planet's size. Now, this planet was observed twice, in 2011 and in 2013. And the weird thing was, it seemed to get a lot bigger. But planets don't get bigger in 2 years. That's not possible, surely. And yet what was seen was 25% increase between these observations. So how does a planet suddenly swell? Well, one theory, before we do that, it also got hotter. So it went from an average temperature of 1,427 to 2,699. And this gave you a clue of what might be happening. One possibility is it's packed full of volcanoes. And during particularly volcanic active times, all the ash rises into the air, blocks out all the light, and the planet looks bigger. And then the volcanism dies away. You can see the planet's surface again, and the planet appears to shrink. Is this true? We don't know. But it's an interesting idea, and it would make the planet more volcanic than anything we've ever seen before. So, what are these worlds truly like? We've yet to find out, but it's going to be more strange than anything you've ever seen before in stories. Thank you very much.
That was a wonderful introduction to some of the strange worlds out there, Elizabeth. Thank you so much. So my question and my part in this talk is, can life really exist under such strange conditions? We have based a lot of our ideas about life elsewhere in the universe using 3 requirements for life: energy in the form of radiation from the host star, or potentially geothermal energy from the planet itself; water that could have been a result of the primordial formation of the planetary system, or potentially delivery by asteroids or comets; and organic molecules. So I ask those of you in attendance here, and maybe those of you online who might want to type something into the chat or type something into the Teams, what are some kinds of organic molecules do you think might exist out there in space? Formaldehyde.
Formamide.
Formamide. That's a complex one.
So you want it simple?
Ethanol. Glycine.
Methane.
Methane, methane, very good. So all of those molecules that were named here in the room have been identified out in space, in interstellar space. In fact, in these large molecular clouds, for example, the ones here on the gaseous pillars in M16. These are regions where chemistry is actually causing these molecules to form, and all the bright pieces that you see on the outside of the molecular cloud are baby stars being formed, such that in 100 million years, all of that gas cloud will be gone and stars will be there instead. We have observed in space sugars, amino acids, and ammonia, in addition to the molecules listed there. So we know that these materials fall on Earth. Hundreds of tons fall to Earth every day, mostly in the form of dust particles, sometimes in the form of much larger rocks. Thousands of amino acids, including 20 that exist in life as we know it, have been found in lots of different kinds of meteorites called carbonaceous chondrites. The Murchison meteorite on the far right is one of these carbonaceous chondrites that was found in Australia in 1969, 220 pounds of material that delivered thousands and thousands of different kinds of amino acids to the Earth. In 2013, the fireball turned meteorite Chelyabinsk streaked over Russia, witnessed by dashboard cams all over the area, littering the Russian countryside with debris and organic molecules. And even here in Scotland, we see evidence for this kind of impact delivery. On the left-hand side is the Stockfada feature near Storr. It is a 1.2 billion-year-old crater that was first discovered in 2008, and it's now been characterized as an impact structure, potentially caused by a 1.6 kilometer diameter object. In 1917, the most recent of the Scottish meteorites was found. This is the Strathmore meteorite, over 32 kilograms total, one piece of it which fell into the roof of the house. And so you can see the animated GIF of the house before and after the meteorite fell through the roof. Most recently in September, there was a fireball that was witnessed by over 200 cameras streaking across Scotland. I heard this afternoon that it actually landed in the Irish Sea, so not seeding the countryside with materials, but instead dispersing that material into the water. So clearly Earth has had and continues to have bombardment by extraterrestrial objects. And life as we know it continues to exploit these niches on Earth. For example, we have thermophiles that have been observed in the hot springs in Yellowstone. Each of those little streaks that you see on the left-hand side are organisms that actually can thrive and reproduce in temperatures more than 225 degrees Fahrenheit. They have a very special mechanism in their DNA that allows them to replicate at such very high temperatures. On the right-hand side is an image of bacteria that has been collected from 1.5 kilometers below the surface of the Earth. This bacteria doesn't need photosynthesis for energy. Instead, it uses carbon and magnesium and other kinds of minerals in its surrounding environment to gain its energy. There are psychrophiles and acidophiles that love acid, barophiles and radiation tolerant organisms, halophiles, organisms that love salt. So things that are very strange and much unlike anything we humans are used to or can tolerate. Some of my favorite are these very strange pieces, are these very strange organisms. On the left-hand side is a 30 million-year-old bacterium that was found preserved in amber. And it basically laid dormant for over 30 million years until a scientist added just a little bit of water to it and it reanimated itself. So it shows how these bacteria, in particular this example, can protect itself in a shell until conditions become conducive again for its own life and for replication. On the right-hand side is an image of Deinococcus radiodurans, which is perhaps the most radiation tolerant organism that we have. It can survive 5 million rads of exposure. How was it discovered? Well, when we humans send spacecraft or instruments out into space, we put it into a radiation chamber to try to kill all of the organisms that humans may have introduced to the building and manufacturing of these spacecraft and instruments. A scientist went inside and swabbed the inside of that radiation chamber. What do you think they found? Deinococcus radiodurans. So we may already be sending radiation tolerant organisms out into space. But humans don't look like blobs of bacteria, right? Could life as we know it, with brains and legs and arms, actually exist around other stars? There are particular zones that we talk about in astrobiology. One is called the Galactic Habitable Zone. And the Galactic Habitable Zone is that region in our galaxy that doesn't have too much radiation, not very close to the center of the galaxy, but also enough heavy metals, so not too far out in the ring or out in the distant arms of the galaxy. We need enough radiation to drive those chemical reactions, and we need enough of those heavy elements to create iron-nickel cores inside of planets, and also to create the to use the other heavy elements for life as we know it. We're also interested in the stellar habitable zone. So Elizabeth touched on this in her talk previously. These are zones around the star, regions around the star where liquid water can exist at the surface. And there are all sorts of different stars out there in our galaxy, and they come in all sorts of different sizes. And the sizes of those stars determine the region of their habitable zone. So on the left-hand side, we have something called an F-type star, which is a very large star that lives a little bit shorter life than something like our sun, which is a G-type star in the middle. And our own star is a little bit larger and lives a much shorter life than something called an M-type star, which is some of our coolest stars out there. They've lived their longest lives, and you can see that they have a very small habitable zone where liquid water could exist at the surface of any planets around those stars. So when we are looking for habitable planets out in our galaxy, we are often aiming for stars where we can detect a habitable zone around an F-type star, a G-type star, or even an M-type star, because those M-type stars have had a long time for life to develop on those planets. The other thing that we're starting to learn based on the moons that we find in our own solar system are potentially planetary habitable zones. So we know that the icy moons Europa and Enceladus could be regions where life could exist in our solar system. They're far beyond the habitable zone of Earth, where Earth is located. Instead, we know that tidal friction from their parent planet, from Jupiter for Europa and Saturn for Enceladus, are causing tidal friction or tugs on those moons, causing and allowing their interiors to stay warm and liquid water oceans to exist at their surfaces. So we're interested now in potentially habitable zones around planets where those moons could actually host life. So there are lots and lots of extrasolar planets out there. I just checked the number this morning, 5,246 confirmed planets. This is up almost 100 since September. So just 2 months ago, we've confirmed 100 more extrasolar planets out there in our solar system. Elizabeth described the Doppler shift that allows us to detect these planets due to the star's wobble as they are orbiting around a common center of mass. And she also described transiting where the size of the brightness of the star dims as the planet passes in front, allowing us to estimate the size of those planets. If these are multiple planet systems, though that star's light dips multiple times, and we can start to extract the sizes of the planets and the orbits of those planets based on how often the star's light dips. There are lots of ways that we're detecting these planets, and the numbers are climbing every day. Direct detection is tricky because we don't often know if what we're seeing is an actual planet, or maybe it's a distant star, or potentially a dim star in the binary system. So here's an example from GJ 758, published in 2009, with the potential of 2 planets orbiting around it, C and B. B was confirmed to be a planet that was 40 times the mass of Jupiter, so far, far bigger than anything we'd ever seen in our own solar system. And C was eventually determined to be a background star. So these are the kinds of interpretations that we need to be very careful about when we're looking at data from stars. The TRAPPIST-1 system is a really, really intriguing planetary system that was recently discovered several years ago. On the top part of the slide, I show you the planets B, C, D, E, F, G, and H. And on the bottom slide, I show you the planets Mercury, Venus, Earth, and Mars. And those of you who are looking very closely can see that entire planetary system orbits around its host star within the orbit of Mercury, right? So they are cram-packed 6 planets all within the orbit of Mercury, orbiting quickly. So Mercury takes about 87 days to orbit around our sun. These 6 planets are zipping around their host star in far less than 86 days, right? So this makes it really, really interesting. And we suspect that several of those planets might be tidally heated by each other due to that tidal friction, due to the tidal locking of those planets around the host star. And if they're warm inside, if they have that energy and they have the energy coming from their star, they could be habitable. We have several planet hunting telescopes that are currently looking for planets out there in space. We have others that are on the drawing table, ready to be designed and launched within the next several decades. Kepler, of course, has been the workhorse for decades, observing over 500,000 stars, confirming more than 2,700 planets, and I'm sure this number is much bigger today as well. In 2018, the TESS was launched. This one is also monitoring over 500,000 stars. It's expected to detect over 20,000 planets of all sizes. Remember, the number as of just a few days ago was 5,700, and now we think TESS might actually observe 20,000 planets. I mean, this is an incredibly large number. And just in the few years that it's been working, we have already confirmed 266 planets from tests, added to that 5,900 total that we have. So I like to paraphrase Sarah Seeger, where she says, so many Earth-like planets, so few telescopes out there. But if we try to think about life as we know it, we still need to understand that life is limited by the laws of physics and chemistry. The chart on the right-hand side is actually a graphic that shows the sizes of stars that have had planets orbiting around them as observed. So the yellow or the off-white circle that you see, that's actually the star, and the little black dot that you see on it is actually the size of the planet in proportion to the star orbiting around it. Jupiter is in the box right under November 2022. So to scale, that is our sun and Jupiter. So you can see that we are really small compared to the other giant stars and giant planets that we have observed orbiting around their host stars. Thousands and thousands of these. This is a very old slide, relatively speaking, but it talks more, shows the number of planets that we think exist within their star's habitable zone. So this chart here is from 2016. The number has certainly increased. Along the top, you can see Venus, Earth, and Mars in the green area, Venus just inside the habitable zone, Mars kind of on the very outside edges of our sun's habitable zone, but lots and lots of other Kepler planets within their habitable zones around their stars. So it makes it really, really intriguing to think about the likelihood of life on these planets. We are finding Earth-like planets in Earth-like habitable zones around their host stars. So then I like to think about the question, well, what's the likelihood of actually finding life, finding intelligent life on another planet? And this approach has been discussed by two people. The first person to come up with this idea was Frank Drake, who recently passed away. In 1961, he was asked by the National Academies, I think it was, to try to estimate what was the likelihood of finding intelligent life in our galaxy. So he took out an envelope and he started writing on the back of it, well, first we need to figure out the number of stars in the Milky Way. Then we have to figure out the fraction of those stars that might have planets. And then we have to think about the fraction of those planets that might have life, that actually have life, that have intelligent life, and life that communicates. So for those of you here in the room, and maybe those of you online who want to type an answer, what do you think intelligent life requires? What kind of life do you think is intelligent? Well, so that's the joke I usually say, right? Depending on who you ask, we ourselves may not be intelligent. Usually when I ask this question, I get answers like dogs. Dogs are intelligent, and dolphins are intelligent because they can communicate to each other, right? So communication seems to be a key form of intelligence. But if we're thinking about communication over the vastness of a galaxy, right, it's not just enough to bark to your neighbor or to chirp across the oceans, right? We actually need to communicate with radio technology. So how long then have we humans been an intelligent radio communicating civilization?
2 years.
Somewhere around 130 years, actually, when Marconi put the first radio signals out there. That's when we started communicating with radio. So for dozens of years now, we've been broadcasting, soap operas and I Love Lucy reruns and Gilligan's Island out into the BBC. I got to remember what country I'm in. Out into the galaxy, right? So we've only been an intelligent communicating civilization for about 130 years. So if aliens came by our part of the galaxy 400 years ago and scanned the region of the galaxy where we orbit our sun and our sun orbits the galaxy, and they would see our blue marble there, they would say, nothing much interesting happening here. Time to move on because we've got 100 billion other stars to look at. So it's that radio communication that we think keys into our ability to be able to detect or communicate with another civilization. So here's another question for you. What are some of these numbers? How many N is the number of intelligent civilizations we would like to try to figure out? So N star is the number of stars in our galaxy. How many stars do we have in our galaxy?
400 billion.
400 billion with a B somewhere. Sometimes 300 to 400 billion is the number that's estimated. Well, how many of our stars are sun-like stars?
About 70% of that, Eric?
Like 10%.
Oh, is it? Oh, right.
Yeah. And then how many of our stars actually have planets around them? Most, right? So 300 billion stars in the Milky Way, about 10% of them are sun-like stars. Kepler told us that pretty much every single star on average has a planet, so we're just going to call that 1.3. But everything else is a big question mark. Right? So depending on if you're pessimistic or optimistic, you're going to start putting in those numbers and calculating your own number. When I do this with my class, I get anywhere from 1 to hundreds of millions of intelligent civilizations out there. Sarah Seeger doesn't care about communicating with those civilizations. She just wants to know if life is out there. So she has published or talked about her own equation, which I call the Seeger equation, where she's just interested in calculating the number of planets with any detectable signs of life. So she's interested in looking at stars that are quiet so that they don't have a lot of extra radiation that might be frying any life at the surface of those planets. She's looking at rocky planets within the habitable zone around their host star. And she's looking at the fraction of those planets that can actually be observed. So we've got these amazing telescopes on the ground and in space, the ones that are being designed that are actually going to be able to extract information from the atmospheres of those planets. And she's interested in calculating and looking at the combination of biogases and the combination of them that could be indicative of life. So we've made a lot of progress since the first exoplanet was announced in 1996, but we still really have no clue if we're alone. And most of these planets are hundreds of light years away, so it would take very, very long times for any of us to try to travel to them or communicate with them back and forth over somebody's lifetime. So she's interested then in looking at the these combinations of gases, carbon dioxide, nitrogen, ozone, methane, maybe CFCs, as we heard earlier today during the science session. But we're still trying to figure out what their surface temperatures are. But to our rescue comes this amazing brand new telescope that was just recently launched successfully, the James Webb Space Telescope. And here are two graphs of the very first atmospheric detections from the big Jupiter planets, the Jupiter-like planets that we have observed orbiting around their host stars. We've identified carbon dioxide, that's on the left-hand side in WASP 39b, and we've detected water in the atmosphere of WASP 96b. So we definitely have the capability of detecting these biomolecules or these gases that we think in the right environment, on the right planet, in the right sorts of conditions could be an indicator of life on that planet. But we have a long way to go. These are very big planets with big atmospheres and big signals. It's a lot harder to get these same kind of signals from the smaller planets, the Earth-like planets with their atmospheres. So then a question like is, where are the aliens? And this is what's known as the Fermi paradox, right? If there are 300 billion stars out there in the galaxy, and we humans here on Earth have invented and developed the ability to travel to space, to send spacecraft out and exploring other parts of our solar system, and even now spacecraft are leaving our solar system. And we have developed radio technology. Why isn't that we haven't heard from other civilizations? Where are they? If intelligent life really existed out there, certainly it could have colonized and done a lot of the things that we have done by now, right? So an answer to that, and I'm just going to throw up a few answers here. You can all decide on your own whether or not which one of these you believe. But one of the answers is, well, the reason we haven't seen civilization, the reason we haven't gotten a detectable, communicated, repeated signal from anyone is because we really are alone. In the 12 billion years of existence of our galaxy and the 4.5 billion years existence of our solar system, we are it. And that can be very enlightening and happy for some people, and it can be very distressing for other people. But this could really be one of the answers. We really are it. We are alone. The second answer to this is that life is out there, but galactic colonization for that species just hasn't yet occurred. We have not started colonizing our galaxy, and we've been doing this for over 100 years now. Very potentially, another civilization is somewhere in the same region of evolution in the same time frame, and they too have not yet colonized the galaxy. And finally, the other one is intelligent life really is out there, but it's deliberately avoiding revealing itself to us, right? Why would it want to get involved with the messes of the civilizations here on planet Earth? It's minding its own business and just keeping its hands off. So these are just some of the questions that have been raised and some of the answers that have been posed by astrobiologists for the last 40 years since the field was essentially created. And it's really, really exciting time. James Webb Space Telescope, other telescopes out there, ones that have yet to be designed and launched, that are currently being designed and have yet to be launched, are going to give us a lot of really, really interesting data. And we got a lot of brilliant minds around the country and around the world, and more brilliant minds coming up through the academic systems to try to answer these questions. So thank you very much. And Elizabeth and I will take any questions now. Thank you. Join me on stage, Elizabeth.
I have a question. Can you hear me?
Yes.
I have a question for Elizabeth. And you talking about the 55 Cancri system with the red dwarf way out on one edge and the planetary system on the other side. Is there an opinion or a finding to whether that is captured or did it form from the same protoplanetary disk?
The red dwarf is not thought to be part of the same system because its distance is really far enough that we wouldn't have thought that it was a brown dwarf, for example, or a plus-sized Jupiter, which feasibly could form in a protoplanetary disk. It is actually far enough away that it's a separate star. So binary stars form in clusters, and binary stars can form that way where two stars form close enough that then they end up orbiting one another, but they're not forming in the same way as planets.
But they are gravitationally bound.
They are gravitationally bound, yes.
There's a question from online.
Yes.
It might also be the case for us being civilization was only formed due to meteorites being water and other organic matter? Question mark.
Can you repeat that, the question?
It might also be the case for us being the aliens, so for us being the aliens, because the civilization was only formed due to meteorites bringing water and other organic matter.
Okay, so there's this idea of panspermia or where life has existed on another planet and was delivered to Earth during meteorite delivery. We do know that Mars was warmer and wetter earlier in its evolution than the Earth was. And if indeed Mars was hit by a large enough object and a little bit of Mars with some life in it came careening into the inner solar system, we just might all be Martians.
Yeah, this is a question for Nicolle. Nicolle, what about the probability that the life form, intelligent life form out there annihilated themselves? You know, it could happen.
Sure. But we couldn't, how would we know that, right?
And what about the other one where they haven't actually evolved into the like our hands and feet are kind of frozen evolution, and they might not have evolved into that kind of hands, and they might be octopus.
No, I mean, there are plenty of answers out there. I just posed a few and I have I think that's entirely possible too. Because 130 years ago or a million years ago, right, we were just now evolving to be intelligent a million years ago.
So I'm just curious, like you mentioned about the James Webb telescope. So can you give some more insights on like how we will be improving upon our understanding using this new telescope in action?
I think that there will be plenty of follow-up observations during its lifetime while it sits out there in space, continuing collecting data. And as interesting signals are being detected, there will be follow-up observations. And I think that the information that we glean from Webb will be forward-fed into other telescopes yet to be launched.
Can I also take an answer?
Yeah, please.
So one of the points of my talk is that we're expecting some very alien worlds, but at the moment we're only really basing that on a global density. So, mass, radius that becomes a volume, you divide them and you get a density. We don't really know. One of the things I'm most excited about for James Webb, but also for Ariel when that's launched by the European Space Agency, is it will start to probe composition. So it'll actually be able to tell us what elements are going into there. And if they're very similar to the Earth, we can say, okay, maybe rock is rock, and the rock we're standing on is going to be typical across planets. On the other hand, if the elements they see is a very different combination of Earth, before we even get started on biosignatures, we might be able to start saying, well, the rock types are going to be really different. The planet core could be different. This could produce more or less volcanism. It could be a crazy alien environment, and we'll start to get some first clues about whether that could be true. I think that's fascinating.
We have another question from the Teams meeting. And I think this is a really good question to actually wrap up on. In case we found life somewhere else in the universe, do we have any plans how to deal with that? I think there's language barriers, scientific evolution, and of course, the famous hostilities.
So there actually is an international organization that is setting policy and discussing how to deal with various communication levels. And that's all I can tell you.
Thank you very much, Nicolle, and thank you very much, Elizabeth. That was brilliant. So, round of applause, please. We'll be back after the break. So, those of you who are on YouTube, you'll find a second link that will stream the next presentation for you all. See you soon. Bye. I think there are quite a few people online. I had some emails to respond to. Does it tell you?
It does.